Pluto stands among the most enigmatic bodies within our solar system. For extensive periods, it maintained status as the ninth planet until 2006 brought reclassification to dwarf planet designation. Its orbital characteristics remain peculiar, elongated and inclined. Occasionally, Pluto positions itself closer to our Sun than Neptune does. This represents a realm of ice and stone, possessing thin atmospheric layers that materialize and vanish dependent upon solar distance. Most remarkable features on Pluto include mountains composed of water ice, plains formed from frozen nitrogen, and even indicators of geological activity. Its largest moon, Charon, possesses such substantial size that both bodies rotate as a binary system. When July 2015 arrived, the New Horizons probe achieved humanity's first close approach to Pluto, flying past this diminutive and distant world that had remained merely an indistinct point through telescopes for nearly a century. Data transmitted to Earth astonished even the most cautious observers. Complex terrain, icy plains, youthful mountain ranges, and the heart, a massive bright region shaped like a heart, designated Tombaugh Regio. However, the most stunning revelation proved different. Increasing evidence suggested that beneath Pluto's thick ice layer, a subsurface ocean might exist. Furthermore, fresh data about Pluto has finally emerged from ground-based telescopes and, naturally, the James Webb telescope, and I'm eager to share this with you. Immediately following New Horizons flyby, research teams began analyzing collected data. Gravitational measurements, topography, mass distribution, and density models indicated that beneath the icy crust, liquid layers might exist. Ice thickness estimates range from 40 to 80 kilometers. Unfortunately, we currently lack such deep drilling capabilities. Nevertheless, an ocean rich in ammonia and salts could exist beneath, which lowers water's freezing temperature and permits liquid state maintenance under extremely low temperatures. Subsequent years brought independent studies confirming this hypothesis. The presumed liquid's density should exceed ordinary water by approximately 8%. This compares to seawater or even more concentrated solutions, like those in Antarctic subglacial lakes on Earth. Presumably, this ocean covers significant portions of Pluto's subsurface layer. Such density helps explain observed mass distribution and supports liquid layer hypotheses. But how could an ocean persist to present times? Heat sources might include radioactive element decay within Pluto's core. Though this source's intensity remains modest, combined with effective thermal insulation through ice shell coverage, it could sustain liquid water existence across billions of years. Additionally, salt and ammonia presence further reduces freezing temperatures, maintaining oceanic liquid states. Ocean existence confirmation can be found in geological characteristics. According to models, certain Pluto regions should have collapsed under their own weight without underlying liquid support. However, these areas appear slightly elevated instead, suggesting support from below. Moreover, Pluto displays structures resembling cryovolcanoes, ice volcanoes erupting mixtures of water, ammonia, and methane. These features might evidence material exchange between surface and internal ocean. The primary question arising when discussing such oceans concerns life possibilities. With water, heat, and chemical substances present, basic conditions exist for simple life forms. Though Pluto possesses extremely limited energy, Earth hosts organisms capable of surviving similar conditions. In Antarctic subglacial lakes, ocean depths near hydrothermal vents. This allows considering even such distant and cold worlds as potentially suitable for microbial life. Potential subsurface ocean presence on Pluto places it alongside objects like Europa, Enceladus, and Titan, moons where subsurface oceans are also presumed to exist. All represent interest not only as geological research subjects, but as potential extraterrestrial life habitats. Who knows, perhaps these amazing creatures already await us. Or perhaps not. Already this year, utilizing observatories in Chile and Hawaii, something unusual was detected for the first time. Pluto's upper atmospheric layers revealed traces of two gases, carbon monoxide and hydrogen cyanide. Yes, carbon monoxide, the same potentially lethal gas on Earth, and hydrogen cyanide, the poisonous gas known from spy films. But what are their origins on Pluto? These gases prove to be byproducts of complex chemistry occurring under solar ultraviolet action. Sunlight, though weak at Pluto's distance, still reaches its atmosphere and initiates chain reactions involving nitrogen and methane. Consequently, new compounds form, rising to upper layers and remaining there, creating distinctive haze. Precisely this haze was captured by our telescope detectors. Most striking is the cooling effect. Hydrogen cyanide and carbon monoxide actively radiate heat into space. This means they literally extract energy from Pluto's atmosphere, making it colder than previously thought. Instead of a simple frozen sphere, Pluto proved an object with dynamic, living atmosphere where subtle battles occur between solar heating and chemical cooling. And there's more. Earth-based telescopes also recorded seasonal variations, haze density, and gas content change over time. These processes are believed to affect its largest moon, Charon. Strange reddish spots have been observed on Charon's surface, possibly connected to these gases settling from Pluto's atmosphere. Meanwhile, Pluto is actively studied by the James Webb telescope. It demonstrated that even such a small body as Pluto can possess incredible climatic subtlety, so delicate that its weather is regulated by atmospheric particles, not cyclones, mega hurricanes, or seasonal currents, but microscopic, chaotic, semi-transparent particles. Molecular dust essentially determines how an entire world's climate behaves, changing almost everything we thought about small body climates. Telescope spectrometry recorded dynamics of these semi-transparent particles, while simultaneously observing how sunlight penetrates Pluto's atmosphere, scatters, and disappears. Not into space, but into these very microparticles and aerosols. Particles measuring tens of nanometers play roles as thermal curtains, absorbing solar heat, redistributing it across different atmospheric layers, managing surface temperatures, regulating nitrogen evaporation processes, forming condensation, and even influencing wind patterns. Sunlight on Pluto is weak, but sufficient to evaporate nitrogen ice, which immediately rises upward, then condenses back. This cycle operates in close coordination with atmospheric particles controlling temperature, thermal capacity, and energy transfer. When discussing climate, we usually envision something constant, average temperatures and stable processes. But on Pluto, climate is primarily variable. It's entirely one large dynamic system. Due to axial tilt and orbital elongation, different surface areas receive varying amounts of solar energy. Sometimes identical points experience coldest winters and hottest summers simply because the sun moves across its celestial sphere along strange trajectories. Then these particles become active. They're regulators, smoothing peaks, distributing excess energy, and maintaining atmospheric stability within possible limits. Most likely, these particles form under ultraviolet action. Solar light breaks methane molecules, which then engage in complex chemical reactions, creating tholins. These tholins not only color Pluto's surface in brownish-reddish shades, but serve as dusty nuclei around which microclimatic structures form. Complex chemistry at the solar system's edge provides us with an entire climatic envelope. If something like this is possible on Pluto, this changes how we'll investigate other small bodies, dwarf planets, trans-Neptunian objects, and large asteroids. We can no longer consider them simply ice and rock chunks. We must think of them as worlds, possibly cold, possibly slow-living, but still worlds with internal processes, climates, histories, and perhaps futures. Now, knowing these subtleties from new research, let's attempt a Pluto surface tour. If we descended to the surface, we'd witness amazing landscapes, true kaleidoscopes of geological wonders. Pluto's surface is solid, firm, with gravity approximately 1/6 of Earth's. You'd feel lighter and could jump about 10 meters upward without special effort, like a space grasshopper. Why? Well, I don't know. We head toward Pluto's ice plains, the most famous location on this cosmic object. They extend hundreds of kilometers, smooth as glass except for gigantic convection cells. These structures result from nitrogen ice covering the plains, slowly mixing like boiling porridge, only at temperatures around minus 230 degrees Celsius. Pluto's ice flows, but on century timescales. Standing in this plain center, the landscape would remind you of a frozen ocean with ice fields marked by strange geometric patterns. Everything underfoot would be slippery, sometimes reddish due to organic compounds settling from the atmosphere. Above the horizon, eternal twilight persists. The sun appears several times dimmer than Earth's full moon and provides no warmth sensation. You stand in eternal winter that nothing disturbs. Nearby stand ice mountains, real mountains thousands of meters high, Norgay and Hillary ranges, named after Everest conquerors. These ridges consist of water ice so hard at such temperatures that it forms stable mountain formations. On Earth, such ice would be fragile, but on Pluto it's like granite. Peaks are covered with frozen debris, possibly traces of ancient volcanic activity. Only this isn't lava, but cryovolcanism, eruptions of liquid ammonia, water solutions, or liquid methane. Perhaps you'd want to climb them, but that's not the best idea. Further, you'd notice canyons and gorges that seemingly pierce the landscape like giant earth scars. Some surface cracks extend hundreds of kilometers and might result from surface stretching, possibly due to internal ice expansion or subsurface changes. This place resembles a fault garden, tectonic activity lines. There are also dark spots, such as the Cthulhu region, named after that very entity. These areas consist of older rocks covered with dark organic substances, Pluto's skin, old and weathered. Interestingly, spending several Earth days there would reveal subtle surface changes. In some regions, nitrogen condenses at night then evaporates during day. You might feel vibrations underfoot or something like muffled echoes in the metallic lander hull. But approaching gorge edges or crack rims becomes more dangerous. Some places have porous ice like frozen pumice. Cliffs and ridges might be prone to collapse. Here you resemble mountaineers on Titanic more than desert explorers. But this world amazes, quiet, alien, and speechless. It lies at light and time's edge, greeting anyone daring to visit with that majestic indifference only space possesses. Yet perhaps someday we'll reach it. Build modules, study this icy wilderness like we once did Mars. And if Pluto ever receives humanity's first step, it will be a step to our solar system's very edge.